Okay, thanks for your questions. So primarily this, for majority of the class, it will be recorded stuff. So I need to watch into camera and tell things. Who didn't get help from graduate student helpers? Everyone else? Okay.
As far as I know, Dylan's the only one that has.
Huh?
As far as I know, Dylan is the only one that hasn't seen Braden yet.
But have you talked to Braden?
Yeah, I talked to Braden.
So, and was it sufficient instructions? Good. So today will be a lucky number of the lab at the evening, if your schedule allows you to visit. And today it will be interesting and important to those who are doing rotational motion. The next Wednesday lab will be the main one when all results are assumed to be completed. Gage and Mike will be main clients, basically. So what have you done last time? Or which subject are you covering?
Rigid.
Yeah, rotation. Which limitations are you imposing to rotations? You already talked rigid, what else? How many dimensions? Yes, but actually there are three. And for practical applications, everyone needs three. It's just I'm surrendering because it's not enough time in this semester to complete it. But there will be some movies to show how the actual solution should be built. So what was the goal of last lecture? Yes. So in order to start new quantum problem, you need to formulate Hamiltonian. And instead of there is no potential, rotation is the same at each angle, and the independent variable will be m. And instead of momentum, the quantity of motion, quantification motion will be angular momentum. Since it is planar, we will have only one component of the angular momentum along axis z, and it is just great luck that it is expressed so simple in respect to angular rotation. In fact, in three-dimensional motion, there are components along x and y, but no one uses them. Instead, one makes conversion to spherical system of coordinates. It makes another angle. But then operators look much more scalable. So if we formulate, we have found that by analogy with kinetic energy, we multiplied combinated enablement by radius of these rotations, and then we introduced the inertia as measure of how much kinetic energy can distort the rotation. And then if you have a Hamiltonian, the natural wish is to diagonalize it. I know it's maybe it's not the natural wish of those who started the course, but you already here for almost 3 months. So when you see Hamiltonian, it is natural wish to diagonalize it, find eigenvalues and eigenvectors. But this is the course of shortcuts and bypasses. Why should we find eigenvalues, eigenvectors of Hamiltonian if you can do something simple? So there are theorems, but at least the practical experience. That you know this high collision, right? So an observable or operator change in time depends on commutation with Hamiltonian. And if the operator commutes with Hamiltonian, if commutation equals 0, it means the operator doesn't change in time, the corresponding observable. Same, there is extension of this principle. If there is an operator that commutes with Hamiltonian, then the eigenvalues, eigenvectors of this operator will coincide with eigenvectors of Hamiltonian. And our Hamiltonian for this two-dimensional rotation would be z projection of angular momentum squared with some factors, and any power of the same operator commutes. So Hamiltonian commutes with L square and with Lz, and therefore it is justified to find eigenvectors of Lz operator, and then immediately start believing that they are eigenvectors of the Hamiltonian. Eigenvectors, eigenvalues will be a little different, but eigenvectors will coincide. Okay, review is done. We are going to actual perspective. So, two-dimensional rotation, eigenvectors of the z projection of angular momentum. So operator, unknown wave function, eigenvalue. What are the units for angular momentum? Well, one can scroll back and find units of anything that comes there, like regular momentum times distance, which is mass times distance over time times distance, so it will be distance squared over time times mass, which is kind of, it's correct but boring. If one continues playing these things, we can realize that the dimension of angular momentum is the same as energy multiplied by time. Mass, distance squared over time. If you divide it by time, it will be same as m squared, units of. So dimensions of angular momentum are the same as energy times time. And on the other hand, what are the dimensions of Planck constant? Same, energy times time. Joules times second, or electron volts times Fembus. Right? And in fact, this is a question that will be legitimate thing to ask Gage when he was presenting. About, I haven't formulated the question, but I do have the answer, and you probably have the idea. Formulation of Bohr's model included the main suggestion that angular momentum of the electron of the circular orbit can take only values proportional to integers of Planck constant. So in fact, Planck constant was introduced as a quantum of angular momentum, quantum of angular motion. Make sense? So if we divide the eigenvalue by quantum of angular motion, the eigenvalue will become of which dimension? What will be the dimension of eigenvalue? Angular momentum divided by angular momentum. 1. no dimensions, dimensionless. So then we will formulate, and we divide left part on the h bar as well. So this is eigenvalue equation, but eigenvalue itself has, there are no dimensions. Okay? So I don't know how about overall physical chemistry, but now everyone who was sitting here last 5 minutes is able to pass test on Bohr's model. Well, what do we do if you see equation? We are trying either to solve or hire someone who can solve it, or find the solution in Wikipedia. So the whole set of bypasses is arranged in order to simplify the differential equations that we need to solve anyway in the physical chemistry and quantum theory. So this is like lowest level of complexity, or like best level of simplicity. Maybe it cannot be simpler. So on the left part, it is first derivative of a known function. On the right, it is a known function. We divide left and right by the unknown function, and divide and multiply left and right by the infinitesimal increment of the independent variable. Then left part depends only on a known function, and right depends on or right on the unknown function, left on the unknown function, and left on the independent variable, right? So one can practice integration of left and right part. Integral of 1 over function will be logarithm, right? Integral of the differential will be just function. And then if one takes exponential with the power of this stuff, it will be logarithm of unknown function will be this exponential of eigenvalue times independent variable. And then if we exponential of logarithm will be function itself. Are we done? Do we have wave function for two-dimensional rigid rotor? Why not?
We only have the general solution, we don't have our boundary conditions.
Perfect. Boundary conditions, and what else?
Initial.
Initial conditions if we propagate forward in time. But here, boundary conditions and something else. Which letters are not known in this expression? So phi is independent variable, we do not need to know. I is known, E is known.
Your coefficient.
So we need the eigenvalue, which we haven't found yet, and we need the normalization constant. Right? So Bill was right. That one needs boundary conditions. But what are the boundary conditions for rotational motion? Other boundaries. What are the like? Is there other boundaries for rotational motion? No. But according to Bill, we cannot live without boundary conditions. So how do we resolve this paradox? How do we set up the boundary conditions for unbound motion? So everyone in this room is already experienced how to do this. We did this approach in the code that we practice in the lab. So if there are no strict boundaries, one can make periodic boundaries. Right? So when wave function is explored along the full cycle. When it finishes, it should reproduce itself at the initial point. So the last point and the initial point should coincide. Otherwise, mathematically, it will be discontinuous function. And discontinuous functions are always bad. Right? And also physically and chemically, it will be some crazy stuff, as we will see very soon. So this was boundary condition for box. So it is 0 at left and right edge. And here we do not specify what will be the value. We just need to set up that after making full rotation, the value of function will be itself. So it can go anywhere, but then it should come into the same value. Okay. Whew. So I do have a local goal for next maybe 10 minutes. Find two values, eigenvalue M and normalization constant C. So since angle changes from 0 to 2 pi, right? Same should be integration, like area of definition of a function. We do not need to know what it will be for 3 pi. So normalization condition is wave function conjugated by wave function, integration over the whole area of definition equals 1. Because of the conjugation changes sign, here these two exponentials cancel each other. And then we have normalization constant squared times integral from 0 to pi or to pi of the independent variable. So then we can solve this equation for C squared times 2 pi must be equal 1 by the definition of normalization. And if you solve this equation for C, you'll have that it is 1 over square root of 2 pi, and the wave function will have normalization constant 1 over square root of 2 pi in front of it, right? Things here were right. I was just not focusing correctly. So right now we have solved for normalization coefficient C, but we still do not know what is the value of M. Well, you all know, because you are so experienced in Bohr theory, right? So what should be M according to Bohr? It's his main postulate. M is eigenvalue of angular momentum divided by quantum of angular momentum, by h bar. So it should take integer values. The amount of angular momentum can take only values of integer multipliers of the Planck constant. Right? So if you solve this, if you continue solving, you should get that M should be equal discrete integer values. It should be very strange if you get something fractional. So how do we get values of M? What you know the rule of thumb for math and equations. Number of independent variables should be equal to number of equations, right? To find the answer. So what will be our equation to find M?
Set that equation equal to the wave function with the boundary condition plus 2 pi.
Perfect. Build plus 1. This equation is already here, right? We just need to plug this functional form into this equation. And then there is a hope that we will solve it and find M. So wave function at argument phi, wave function at argument phi plus 2 pi. And this equation comes from intuitive understanding of boundary conditions for unbound rotational motion. We have the continuous wave function everywhere. So what can we do here? We can cancel normalization, and we can cancel e to the power im phi. Then our equation is here. 1 equals e to the power 2 pi im. Is it possible to solve this equation? M is only unknown variable. Okay. So how many answers this equation has? Well, the trivial answer will be 0, right? E to the power 0 will be 1. So no rotational motion is a good solution for rotational motion. And as chemists, you agree with this because you know about S orbitals. Okay? You don't have a rotational component. But can it be values of M that differ from 0? So how do you know?
Euler.
Perfect. Then or Euler plus 1. So according to Euler, we expand the imaginary exponential into sum of real cosine and imaginary component is sine. And it should be equal, so it is a complex number, right? But 1 is also a complex number, because real part equals 1 and imaginary part equals 0. Theorem. 1 is a complex number. Sure. So how do we solve this equality? In fact, it is it can be decomposed into 2 equalities. So real part is equal to real part, and imaginary part equals to imaginary part, right? Cosine 2 pi m equals 1. 2 pi m equals 0. And these two equations should be solved simultaneously. So on the x-axis we can put the value of m. That by now we do not know what it will be. Hypothetically, we can assume that it is also takes fractional values. But it should be cosine. Sine should be equal 1. Right? Here will be cosine. And cosine equals 1 when argument of the cosine equals to pi. Or multipliers of 0, pi, 4 pi. Sine will be 0 when it is equal to fraction of pi. 0, pi, 2 pi, 3 pi. But we need to match both equations. So we will take only those points where this coincidence. 0 plus minus 2 pi plus minus 4 pi, right? Just to match these equations. So we can cancel 2 pi on the left and right and get the answer that m is equal 0, plus minus 1, plus minus 2, and so forth. Amazing. How do we interpret what you got? So it was a little mathematical exercise with Euler, but in fact we found eigenvalues of angular momentum. And according to our beliefs, it will be at the same time when we use these eigenvalues and reconstruct functions, they will immediately become eigenfunctions of the computational motion. So, in some sense, by looking on the two-dimensional rigid rotor, we are rediscovering Bohr's model. So that only discrete values of angular momentum proportional to these integers are permitted. This is not the whole Bohr's model. It has another component because here we are not telling about the we are having rigid rotor and we are not changing the distance. The Bohr's model also solves for distances. It does it not in a quite correct way. It uses classical electromagnetic induction connection between centrifugal force. From modern point of view, it can sort of so eigenvalue m equals this integration numbers, and then we plug in this m into the function, and now we can use this eigenfunctions of two-dimensional rotational motion. Whew. What is most important? Can this eigenvalue be fractional? What would happen if we plug in fractional number m? Like we have who can forbid us to use fractional value of m? As free people, we are ready to follow to face the consequences, but what will be the consequences? Tries to put fractional m. Any suggestions? It's a special question for who is absent and for gauge who is present.
The shape of the electron power per wave will change for fractional.
It will change, yes.
It will change shape, but it won't be 90.
Yes. Do you hear it? So the eigenstate of coming means that if we prepare a system in this state, we probably got enough credit, but so if we prepare a system in the eigenstate and let it propagate forward, then the eigenstate will not change. The states you make it move and it's like a standing wave. Where do you see standing waves in the daylight? if you put a cup of coffee on the working car or the washer and dryer, it changes. That change very easily. So eigenstates are standing values. Right? If you will prepare a state that is not an eigenstate, and you let it go according to time-dependent equation, the shape will be changing in time, which is an indication that this state is not an eigenstate. Another way to solve this eigenvalue problem is to arbitrarily guess any crazy function, plug it in numerically, and see whether it will stay stationary or not. Make sense? This figure before. Restart. So here the angle phi is going along the circle, and this double line is 0. The green and dashed lines are real and imaginary parts of the wave function. In left panels, one has plugged values of m and 3, and on the right, one has plugged in the fractional numbers. So if our discussions were correct, it is expected that this 2-petal form and 3-petal form will be conserved as we go forward in time. And here, the shape will change at any instant of time. It will not, maybe the rotation is nature of rotational motion, but the shape, these ranges will take u and u form each instant. So if you see, the shape didn't change, which indicates that it was an eigenstate. And here it was like changing not only orientation according to angle, but the shape. So it's not forbidden. You can use fractional m. Then it will be not an eigenstate. That's it. And not eigenstates are in fact superpositions of eigenstates, as we considered before. Okay. So we do believe that eigenfunctions of commuting operators are shared. The eigenfunction of angular momentum will be the same as eigenfunction of Hamiltonian for rotational motion. But the eigenvalue of energy will be different. So we need to practice bra and ket. So put our eigenfunctions, which are this exponential with e to the power I m phi on the left and right, and put Hamiltonian in the middle. Hamiltonian is, what was it? It was very similar to Hamiltonian of the free space. This operator to our oscillating exponential. the only thing that by taking derivative of the e to the power I and phi, we will pull eigenvalue to the front. When you take derivative once again, you put this eigenvalue once again, right? So by practicing this operation, you get constants times m squared times function percent, function unchanged, m squared. And then if you multiply it from the left by the same function and integrate, wave functions will be removed due to which property? Orthogonality, right? And the only thing will be m squared with some factors. The factors will be h bar square and two inertias, right? So now we have achieved another milestone. We have found eigen values of energy operator for two-dimensional rotation, right? So this parameter or eigenvalue of angular momentum takes integer values, and energy takes constant h bar square or inertia times m squared, square of this angular momentum values. I don't know about you. I'm always failing in doing things with dimensions, and it is natural wish to play with variables in dimensionless system of coordinates. So what if we divide left and right part by h bar square and by 2 inertia? We'll get dimensionless energy of two-dimensional rigid rod. Right? So eigenvalue of energy divided by constant will be m squared. So let's analyze what we have. So on the x-axis, we do have this dimensionless eigenvalues of angular momentum, right? Integers. 0, plus minus 1, plus minus 2. On the y-axis, we do have energies of the rigid rod. So what should we look at? What is important here? How many quantum states have energy 0? 1. How many states have energy 1 square? 1. 2. How many states have energy 4? 2. Good. This is correct answer for two-dimensional rotation. If you are taking notes, record it. So for each quantum state except ground state, there is a degeneracy. So each eigenstate is 2 degenerate. Whew. Now I'm going to fail my own rules and present something that we didn't derive. So how does this rule of degeneracy will be followed or violated if you consider three-dimensional rotation? So there will be a big analogy. A lot of things will be similar, but it will be different. So the energies, dimensionless energies, will be following very similar trend. But the main thing that one would observe by looking on solution for three-dimensional rotation will be degeneracy. So degeneracy for states with higher and higher quantum numbers will not stay equal to, as we had here, but it will grow. So it will be another point here, 3 degeneracy for first state, 5 degeneracy for next one, 7 degeneracy for next one. As a consequence of three-dimensional rotation. Two things. how to wrap our mind around this additional degeneracy, and second, who needs degeneracy? When do we need it? So this degeneracy is needed if we want to predict outcome of rotational vibrational spectrum. You remember the stuff is 2 wings. It's critical. Where does it come? Okay, I'm going to show this degeneracy that grows. 1, 3, 5, 7. But let's look on solutions. So I'm going to illustrate the YouTube link by someone else that I sent this morning. So right now, I'm going to show images and speak words without direct equation. So when one tries to solve for three-dimensional rotation, there will be progression of energies that also goes almost quadratic. And for each value of energy, there will be several states that have the same energy but different values of m, different values of angular momentum projection onto z-axis. Try to record it if you are taking it. So for three-dimensional rotator, there will be states with the same energy but different amount of rotation in our 2 dimensions, different value of projection of angular momentum onto z-axis. In the illustration, there will be about 6 slides. I'm selecting set of such states. They all will have value of total angular momentum 5, and this dimensionless energy will be 25. But then I will show how the three-dimensional wave functions will look like for different projections of the LZ. Different amount of rotation in the plane, XY plane. So for three-dimensional rotations, we have our phi angle in the XY axis, and there will be another angle theta that goes from y to x axis. And wave function will be three-dimensional. There will be lobes and nodes in this shapes. So one of them has nothing being changed as we go in a circle around phi. But as we go along the theta angle, there are changing lobes and nodes. So total 1, 2, 3, 4, 5 lobes. You know, I already have seen it. Everyone in the class knows that fringes of wave function correspond to motion, momentum or angular momentum. So we do not have fringes as we go in circular, but we do have fringes as we go along this angle theta. It means it will be rotation along x and y axis, but nothing along z axis. So one lobe, no nodes along angle phi. Next one. 1, 2, 3, 4 lobes in the theta angle. And then if you go circular along phi, you have 2. One maximum, one minimum, 2 nodal points. It means there is one full cycle and there is some slow motion around the x and y plane, this projection of angular momentum in z direction. So maybe 4 floors with, populated with this pattern. Now, next one. Along theta direction, we have 1, 2, 3 lobes. It means less motion, less rotation in x and y direction. And in rotation around z-axis in xy plane, there is 1, 2, 3, 4 lobes. They change sign, which means 2 full cycles. So more motion around z-axis in xy plane. It's same energy, but different amount of motion around specific direction. Quantum number m equals 2. Next one. See, less motion in theta direction, only 2 sets, one positive, one negative. And then if in each of these subsets we are going circularly, it has 6 lobes or 3 full cycles. So it will be m equals 3. More motion along xy around z direction, less motion in x and y. And here there is no motion around theta direction, but a lot of motion around z in xy plane. So 4 full cycles. This one means all angular momentum is going for this 2-dimensional motion. Okay? So you have seen this, right? So it's solutions of 3-dimensional rigid rotor. And you do know that projections of M goes from takes positive and negative values. So we considered positive, but there are very similar taking negative values. And for given total angular momentum equals 5, there will be 1, 2, 3, 4, 5, 6, 7, 8, 9 degeneracy. So all of the states have the same energy, but different projections of angular momentum. So here is I need to rerun so that the movie will run. This is the stuff that was sent to you. So it is artistic design by someone else, but it's an introduction. Okay, so different values of energy, total energy of rotational motion. And for each value of energy, there are several states which differ by amount of rotation in xy plane. So the larger number of these lobes, the quicker the rotation. So this illustrates this figure. For each energy, there is a degeneracy. The difference of this dimensionless things that we index our states by 2 numbers, and instead of m squared as we consider for 2-dimensional, it will be L times L plus 1, almost L squared. Okay? You see this equation again and again in different courses for vibrational spectroscopy. So, it's about time to stop. Let me summarize. Overall angular momentum. Degeneracy, number of states for given energy. 1, 3, 5, 7. 1, 3, 5, 7. Dimensionless energy, 0, 2, 6, 12. Energy offset between growth. This information can be plugged into definition of absorption spectrum, which includes the operator of transition and energy difference. And this would explain this shape of vibrational spectroscopy. Thank you for the patience. Hope that some of you have energy to come 5 p.m. QVB 132. Those who do not have energy have a happy Thanksgiving. See you tonight, and maybe a larger attendance on next Monday morning.
have a question on in the project. Excuse me, in this project report.
Uh-huh.
Basically, the content thereof. Like how long are you expecting the report to be?
4, 6 pages. Well, if you count like 4 pages without figures. With figures, you can, if you take a figure for the whole page, you can expand it to like 20 pages immediately.
But so you want like an introduction and background that we like for chemistry, or just
A little.
Okay.
Please send me a reminder and I will share the examples how it was. Examples from previous years.
Okay.
The students who reported on electrochemistry in previous years were not at the top of the class, so you do not be careful and do not
Build upon.
Yes, build up. Exactly.
Okay.
Then,
I like having more somewhat of a rubric type thing. What is?
okay. So the idea is that, well, it will be great if we do something tonight.
Yeah.
I will present something, but next Wednesday, it will all results should be completed. And on Friday, well, not the coming Friday, but second. Not the Black Friday, but next one.
Break down the door at 6 a.m.
Yeah, everyone is expected to bring first draft of the written report.
Okay.
So it's about 10 days from now.
So presentation next Wednesday.
Not
presentation.
Not presentation.
Yes.
Report first, presentation second.
Okay.
So second Friday from now, written report. First Friday from now is Black Friday.
Yes.
Second Friday from now is written report.
Written report.
Third Friday from now, presentation.
Okay.
Okay.
Thank you.
I do plan on coming to the meeting tonight. I just might be a few minutes late.
That's fine.
Yeah, I'm doing some research until 5, so I should probably be out of there sooner. But I'm doing some research at CPM with the Elena Shafranska. Yep, so might be a little late, but I'm still planning on coming. So
Okay.
yep, see you later tonight then.
Yeah.